So we've learned something about the chemical shift. There are different regions of the spectrum that are commonly referred to in organic chemistry. So the region towards zero is called upfield. The region around 10 or below is called downfield. So these are just terms to differentiate if a chemical shift is upfield or downfield. Let's take a look at the major functional groups which we've learned over the course of the semester and see where they lie on this chemical shift axis. So let's start down from 0 or upfield and then work our way towards 12 downfield. So in the upfield region are saturated carbon. So we're talking about the proton here. So we're looking at sp3 type carbons. So sp3 hybridized carbon, their hydrogens occur between 1.5 and 0. So that gives us an indication if we have an alkane, it's going to occur between 0 and 1.5 parts per million on the chemical shift scale. So moving downfield, we have allylic. So we've learned two types of allylic situations. We can have a CO double bond, and then this is the allylic carbon here. These hydrogens, or carbon-carbon, these hydrogens occur between 2.5 and 1.5. So we've differentiated the situation in which, or the environment in which these hydrogens reside. These are allylic, so allylic to a CO double bond or allylic to a CC double bond. Moving more downfield in the region of 2.5 to around 4.5. These are hydrogens bonded to carbon, which is bonded to a heteroatom. So you have a carbon bonded to, say, some heteroatom X. These hydrogens occur in this region. So what is X that we've learned? So nitrogen, oxygen, fluorine, chlorine, bromine, iodine, the halogens. So now we're moving more downfield again. So between 6.5 to 4.5 region of the chemical shift scale, we have hydrogens bonded to sp2 hybridized carbon. So this hydrogen's bonded directly to an alkane. We call that vinylic. So another vinylic type hydrogen are the aromatic hydrogens. So hydrogens bonded to a benzene ring. So sp2 hybridized, these are called aromatic. These occur between 8.5 and 6.5. And then finally, between 12 and 9. So 12 is pretty much the limit in proton NMR. And 9. Typically out here you'll see aldehyde. So here's our general aldehyde functional group. You'll see this hydrogen. Additionally, you'll see acid, CO2H, this hydrogen. In the acid, this acid hydrogen typically occurs as broad. In the aldehyde, it's fairly narrow looking. So what we've seen for proton NMR is that over the chemical shift range from 0 to 12, the functional groups are spread out. They don't all occur in one region. So let's go ahead and look at the carbon-13 NMR now. So the first thing to notice is that the scale is much larger. So instead of 0 to 12, as we saw in the proton, we're now 0 to 220. So we can use that to our advantage because there's going to be greater distance between functional groups on this scale. So let's start down in the upfield region here. So these are going to be the saturated carbons. So we're looking at the carbon functionality now. So a typical sp3 hybridized carbon in an alkane. So these you'll find in the range from 40 to 0 parts per million. Where we're again moving downfield, so again this is downfield as well. We're going to find carbons bonded to heteroatoms, so CX, where X is equal to nitrogen, oxygen, or halogen. So heteroatom bearing carbons. These occur between 60 to 30. So notice there's a little bit of overlap here in terms of these ranges. So the next region we encounter in terms of functional groups from 60 to 90 parts per million are alcohols. COH. Moving further downfield, we hit the alkynes. These are the sp hybridized carbon. So these occur between 100 and 80 parts per million. The next region we'll see are sp2 hybridized or vinylic. So CC double bonds, alkanes, 150 to 100. So your typical alkanes here. Another term for that is vinylic. Again, kind of mimicking what we saw in the proton NMR, we're going to now hit the aromatic. And what I mean by aromatic is a benzene ring. So a carbon in a benzene ring will occur from pretty much the same region, 150 to 100. They're both sp2 hybridized. And then finally the last region, the type of carbon that we're interested in is, say, 220 to 170. And these are the sp2 hybridized carbons of a carbonyl. You'll see some resolution between aldehydes, ketones, and esters in this region. But generally, this carbon falls in that region. You can then use corroborating evidence from the infrared spectrum to determine exactly what type of carbonyl that is. So this has been a tutorial screencast on functional group location in the NMR spectrum. We've seen a couple features of the NMR spectrum. We're looking at chemical shift, Greek letter delta, with the units of parts per million. In the proton NMR, it runs from 0 to 12. We have good separation of the functional groups. Carbon-13, it runs from 0 to 220. And the functional groups mimic what we see in the proton NMR fairly well in terms of hybridization.